advisors, not just for inviting me to speak, but also for putting this together and having it be a very pleasantly positive surprise in all the bad that's going on right now. So this is joint work with Bernard Bargmann and Donald Corey. They were my PhD advisors. And this was actually inspired by John Clotter. He, not just because of the work he's done in this field, but he actually posed this problem during my PhD defense at the very end. And it actually blossomed into a full theory. So before I begin, I want to just do a quick recap of the oscillator algebra. Many of you are probably familiar with this. So given a Hilbert space H and an operator A on H, the oscillator algebra is a Lie algebra generated by A star, and A star A if it satisfies these three conditions. This one here, the leftmost, is actually basically the Heisenberg-Weyl relations, and the Heisenberg-Weyl algebra is a Lie subalgebra of the oscillator algebra. The other two are basically creation and annihilation conditions. The middle one says A is an annihilation operator. The other is creation because of the plus and minus one aspect. And this isn't only generated by these four, but these are actually a basis. The generalization beyond what I present here actually has an issue with this. So you can actually find a representation of this on any separable Hilbert space. Non-separable things get a little bit tricky, obviously, but you can do, given the orthonormal basis En, you can define A on E0 to be 0, and then A on En to be square root n En minus 1. And then that immediately tells you that A star on En has to be square root n plus 1, En plus 1. And then A star A is diagonalized by the basis. And eigenvalues are 0, 1, 2, and so on. So this is a nice abstract representation of the oscillator algebra, but we actually have a well-known concrete representation on L2 of R. And that is given by taking A to be 1 over square root 2 d by dx plus x, effectively. Different people choose different normalizations, but not a big deal. So you have to do a little bit of domain of definition checking here, make sure things are well defined. I'm going to do that briefly on this slide and not do it anywhere else because I would not have enough time. But on these functions, we have a nice representation for its adjoint, and it's basically 1 over square root 2 negative d by dx plus x. The sign change is very important for what I will discuss shortly. And then A star A is the well-known quantum mechanical Hamiltonian for the harmonic oscillator. There's this little phase shift on the far right, and that's just to make the eigenvalues 0, 1, 2, 3, instead of 1/2, 3/2, 5/2, and so on. So this has a nice diagrammatic representation. So starting at the lowest rung, which represents the eigenvalue, the eigenfunction with eigenvalue 0, A star then takes you up one level, and then another, and another, and another. A then takes you down a level, down a level, down a level, until you get to the lowest eigenvalue state, at which point it annihilates it. There's nothing left. And yeah, as I said, these represent the eigenfunctions of A star A. Okay. So that's one representation. There's another that's partially suggested by the L2 of R representation. So before I get there, I need to define what a holomorphic function space is, since it'll be very important for what's to come. It's a vector space of entire functions, typically, or holomorphic, I should say. I don't know why I said entire. It's entire for what's to come, but it's a vector space of holomorphic functions equipped with an inner product. And then when you do a completion, it forms a Hilbert space. So some examples are the Bargmann space, typically on the unit disk, and then the Siegel-Bargmann space. The Siegel-Bargmann space is what I'm going to focus on because that's what I'm working with, Bargmann transforms. So the connections between the L2 of our representation of the oscillator algebra and x and d by dx kind of suggest another representation. So d by dx and x have a commutator of 1, but x is a symmetric operator, whereas d by dx is anti-symmetric. So if you try to have d by dx represent the adjoint of x, it's going to fail because x is symmetric and they don't agree anywhere. So how can you rescue this? Well, the obvious answer in hindsight is to then go to the complex plane. Because on the complex plane, z is not a symmetric operator because z and z bar are in general different. So define the measure d rho to be 1 over pi e to the negative Gaussian times the area measure. And then on the space of entire functions with the finite L2 norm with respect to this measure, it turns out that A given by d by dz actually can have adjoint given by z. So this issue that existed in the real case because x is symmetric is rescued in the complex case because z is not self-adjoint. And I guess as an equation, you do an integration by parts. You have to do a little bit of Stokes type argument, which isn't hard. Boundary term goes away and you get a factor of z bar. So that gives us the adjoint aspect, but that doesn't quite tell us how to get from L2 of R to L2 of C. The Bargmann transform will do that for us. And it is an isomorphism between these two representations. So the unitary map B defined as this, you'll notice that there's a normalization factor, doesn't really matter too much. That's just to make it unitary. There is a Gaussian in Z and a Gaussian in X, and then there's an exponential part in the middle. The outer two pieces are fine, but what will change significantly is the inner piece. And this operator satisfies that B of the annihilation operator in X is the annihilation operator in the Bargmann space, and then B of the creation operator in X in R space ended up being the creation operator in the Bargmann space. So this can actually be, and I denote the Siegel-Bargmann space as OL2. This is just holomorphic functions on L2 with respect to this measure. These two relations can actually be summarized with the following diagram, commutative diagrams. So we have A going from L2 to L2, obviously domain of definition issues everywhere. And then the Bargmann transform takes us then to the Bargmann space in both, but what A represents in the two different ones is different. So on top, that's the real line representation, the d by dx plus x with the square root 2. And then on the bottom, that's your d by dz. Similar happens with the adjoints. It goes from 1 over square root 2, negative d by dx plus x, and then down to multiplication by z. So that's a quick recap of regular Bargmann theory. Now I'm going to talk about coupled supersymmetry. So let H1 and H2 be Hilbert spaces. And then there's some, again, domain of definition issues. And let gamma and delta be real numbers. I say that this ordered quadruplet A, B, gamma, delta forms a coupled SUSY if the following two hold. A star A is BB star plus gamma, and then A star is B star B plus delta. So the oscillator algebra is actually a special case of this by taking b equal a and gamma equal -1 and delta equal 1. Again, I omitted some details for brevity because the details would take up an entire slide, most likely. So much like the oscillator algebra, there's actually a Lie algebra that underlies this, or two actually, because there are two separate Hilbert spaces and there's an algebra on one and an algebra on the other. So this top one is actually the algebra on H1. And you can see there's some creation and annihilation operator conditions on the last two equations. And then the top one is actually just the commutator of the raising and lowering operators. And that luckily just gives us a linear function in A star A. And then we have a very similar set of equations on the Hilbert space H2, and it's the same, basically just reorient the operators. Works out kind of nice that way. And these are actually isomorphic to SU11. That actually helps a lot with what I do for work. And A star A has eigenvalues m times delta minus gamma, and m times delta minus gamma plus delta. And once you know the eigenvalues of A star A, you know the eigenvalues of AA star up to maybe an eigenvalue of 0. And then you can say the same about B star B and BB star because of the coupled equations. So that's enough. So diagrammatically, this can be represented as follows. Now these rungs are represented by eigenfunctions of A star A and AA star. So A and A star just move left and right, but then B and B star kind of act like knights. They move over 1 and up 2, or down 2. So over and up 2, to the left and down 2. If you did B and B star B and B star, they would switch roles. So there's a concrete realization of these on L2 of R in a special case, and it's given by these with gamma equals -1 and delta equals 2n minus 1. These two numbers are kind of like the defining aspect of the coupled SUSY. If you take n equals 1, this does give the usual oscillator algebra. If you take, because then B is A and gamma is -1 and delta is 1. So the Bargmann transform should pop out. There's actually holomorphic representations, and those are nicer than what we just saw. So I define these two function spaces. I use F because of the Fock space being so closely related to Siegel-Bargmann. And notice that I skipped terms in the series. Usually the Bargmann space has all powers of Z. I have to omit some. And the closure is taken with respect to these. K here is the K Bessel function. It's horrible, don't worry too much about that, but just know it's positive, or rather non-negative, so it's a good measure. And then same thing for F2. The only difference is the order changes on the Bessel function. And these are actually radial, so that Zm and Zn are actually orthogonal if n and m are different. So that's a nice thing that you want. And on these spaces, now that we've defined the spaces, we can define the operators. An takes a much simpler form. It's just 1 over z to the n minus 1 d by dz, and its adjoint is multiplication by zn. Bn similarly is just the reordering of the operators for an, and then its adjoint is just zn. So things are much cleaner here. It's easier to talk about domain of definition and so on, which is one of the huge perks of the Bargmann space. It takes a lot of the hard functional analysis and makes it easier. So now let's try to find the isomorphism between them. So I define two different Bargmann transforms because we have two different Hilbert spaces and two different Siegel-Bargmann space generalizations. And they're defined by community diagrams as follows. just like before, but now we have actually 4 diagrams because we have 4 different operators to work with. And same thing with the adjoints. And what you get using some Riesz representation theorem arguments is they're actually integral transforms with integral kernels, and the integral kernels satisfy some really terrible partial differential equations. These are easy to find. What's not so easy is to solve these. So after X pages of algebra, we can write the Bargmann transforms as such. The tau n is a really terrible normalization constant to make it unitary. Just know everything is okay. The main takeaway here is we get something that plays the role of a generalized Gaussian. So it's z to the 2n over 2n. And the same thing with the exponential with x. But now that square root 2 e to the square root 2 zx has been replaced by something that looks like the integral or the measure, except instead of it being z bar z, it's negative zx. And when n equals 1, these exactly drop down to the Bargmann transform. They're actually also reproducing kernel Hilbert spaces. And you do the usual thing, anti-holomorphic in Z, holomorphic in W, and then just multiply them and divide by the normalization. These coefficients are terrible. I will not write them down because it wouldn't even fit on one line with one term. So given f in f1n and g in f2n, we can reproduce them via k1n and k2n. So this, I've developed a theory, but now I don't actually, I haven't explored applications of it yet. So the Bargmann transform has been used in the study of the backwards heat equation, kind of solving it backwards in time to some extent, not super much so, but kind of getting some analysis on that. So in theory, the coupled Susy-Bargmann transform should be able to do the same with a different PDE. Here, the Laplacian will get replaced by something like d by dx, 1 over x to the 2n minus 2, d by dx, and then something very similar to that. And then another one is the Bargmann transform for people that are signals based. It's effectively a short time Fourier transform with a Gaussian window. And if you leave the Fourier setting, short time transforms actually get really nebulous because part of the key to the short time Fourier transform is the translation aspect that is important to the Fourier transform. I developed one analog, and I only really realized recently that this does not match what I had done in a previous paper. So this kind of gives you 2 different analogs of a short time transform for studying signals. So here's some further questions. What happens if n is non-integer? Do integrals over C need to be replaced with infinite sectors instead? If you have like an nth root type problem where you don't want to cross over a branch cut and lose analyticity, can we still get unitarity? What plays the roles of translation and modulation with the coupled Susy-Bargmann transforms? And is there an analog of the Heisenberg group? Can the distribution theory of the coupled Susy-Bargmann transform be used for worse distributions? Because there's that e to the negative x to the 2n over 2n. That can take worse distributions than the Bargmann transform. So could you work with stuff, could you do backwards heat equation stuff with this? And then some others are there peculiarities if you go to the Fock space when it comes to coupled Susys? And what happens if you combine for different values of n in the same Fock space? What happens to the analysis there? And that's the end of my talk.